Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video, and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is session 18. In this session, working of a DC motor, back EMF, torque equation, speed relations, and a few worked examples. These are the topics covered. Now the basic principle of a DC motor is that when a current carrying conductor is kept in a magnetic field, it experiences a force. And due to this force, it starts rotating. And the direction of this force can be determined by Fleming's left-hand rule. We are familiar with this. See this figure, armature is kept in between two magnetic poles. Now we are applying a voltage across the motor terminals. Now a current will pass through the field winding. So that will produce the necessary magnetic flux. And also a current will pass through the armature conductors. Now the basic requirement is satisfied. That means a current carrying conductor comes in a magnetic field. When we apply voltage across the armature, when the motor terminals, a current will pass through the field winding. So this will produce the necessary magnetic flux. At the same time, a current will pass through the armature also. So armature conductors are carrying current, and armature is in a magnetic field produced by the field poles. Now the requirement is met. That means current carrying conductor comes in a magnetic field now. It experiences a force. So here current direction is marked only in one conductor, but current passes through all the conductors. So due to the combined effect, it starts rotating. See in this figure, this is the north pole, the south pole, this is the magnetic flux, and here current direction is marked in this particular conductor. It is inward. Inward means towards the plane of the paper. Now, accordingly, if we determine the direction of force using Fleming's left-hand rule, so this is the direction of magnetic flux, current is inward, we will get a force in this direction. And if we mark the force experienced by a conductor in the bottom half, we will get it in the opposite direction. That means the torque is like this. It starts rotating in the counterclockwise direction. All the conductors experience force. So it starts rotating in the counterclockwise direction in this particular case. Now what happens is that a conductor is moving in a magnetic field. Armature conductors are moving in the magnetic field. Now when a conductor moves in a magnetic field, an EMF is induced in it. So if we mark, say here the diagram is drawn again, it's direction of flux, direction of force, direction of current. So the magnitude of this EMF is same as in the case of generator, pi Z then P divided by 60A. And if we determine the direction of the induced EMF, for example, in this case also, if we determine the direction of induced EMF, it is opposite to the direction of current. See, here current is inward, but the EMF is outward. So the diagram is redrawn here. Flux, current, force. Due to this force, it starts rotating. Here it is rotating in the counterclockwise direction. So an EMF is induced whose magnitude can be obtained by this equation. EB is equal to 5ZNP divided by 60A. And its direction can be obtained by Fleming's right hand rule. And it is like this. It is marked in red ink here. It is opposite to the direction of current. So that is why it is called back EMF. So the EMF induced in the motor conductors is called back EMF. So the direction, the motor diagram can be drawn like this: field, armature resistance. This is the back EMF. So the electrical equivalent is like this. We can, for analysis sake, we can redraw the motor circuit like this, or it is equivalent to this. These are the motor terminals where we apply voltage. This is the field. So the armature circuit, armature resistance, and this is the back EMF. So since the voltage induced in the armature conductors when it is rotating is in a direction opposite to the applied voltage or opposite to the direction of current, it is called back EMF. Its magnitude is 5ZNP divided by 60A. So this is the motor circuit diagram. V is the applied voltage. I is the input current, or current taken by the total current taken by the motor. IA is the armature current. IF is the field current. So from this diagram, we can write I is equal to IA plus IF. So the current taken, total current taken by the motor is the sum of armature current and field current. And also from the equivalent diagram which I have drawn here, this is field, this is armature, RA, this is back EMF, EB, this is V. So this current is IA. The voltage drop in this resistance is IAR. So we can write V is equal to EB plus IAR. So this back EMF is in a direction opposite to that of the armature current or applied voltage. So the applied voltage is sum of back EMF plus voltage drop in the armature resistance. So two relations we can write here in the case of a shunt motor. I is equal to IA plus IF and V is equal to EB plus EAR. Now next is the torque equation. So let's assume that TA is the magnitude of the armature torque, net torque experienced by the armature. So power is equal to, we know that power is equal to force into velocity. But in this case, it is rotating motion, so power is equal to equivalent. Instead of force, it is torque, and instead of linear velocity, it is angular velocity. So power is equal to force into velocity. In the case of rotating motion, it is torque into angular velocity. So TA is the armature torque, into 2 pi n. N is the speed in RPS. So many revolutions per second. So TA into 2 pi n. That is the power developed by the armature. For power is equal to torque into angular velocity. So torque is armature torque. We are assuming as TA and into 2 pi n. Speed is defined. So here n is the speed in revolution per second. Also another equation for power developed is EB into IA. EB is the back EMF, IA is the current taken by the armature. So the power developed by the armature can also be written as EB into IA. Now we can equate this to 2 pi n TA is equal to EB is 5 ZNP by 60A into IA. So rearranging we can get armature torque is equal to 1 by 2 pi 5 ZIA into P by A. Usual notations in Newton meter. So we are developing two equations. We are writing two equations for power developed by the armature. So in terms of torque, it is 2 pi nt watts. 2 pi, but n should be in revolution per second. 2 pi n into armature torque. That is the power developed by the armature. Also, the power developed by the armature can be found by multiplying EB with IA. Back EMF into armature current is the power developed. Equating, we can get torque is equal to 1 by 2 pi 5 ZIA into P by A. Now, torque is equal to 1 by 2 pi 5 ZIA into P by A. The rest of the parameters are constant in this equation except phi and IA. These are the only two variables. So, other than phi and IA, TA is equal to 1 by 2 pi phi ZIA into P by A, Newton meter. So number of poles, number of parallel paths, number of conductors, etc. are constant for a particular machine. So we can write torque is equal to phi into IA. But for shunt motor, phi is constant only. So during its operation from no load to full load, we are not changing the field current at all, or we are not varying flux. So flux is constant. So the relationship is direct torque is proportional to armature current. But for series motor, flux is proportional to armature current. Series motor is like this. This is the current, which is field current, armature current, input current, all are same in this case. So the flux produced by the field is proportional to armature current. So we can write, instead of phi, we can put IA there because phi is proportional to IA. You can write torque is proportional to square of the armature current. So this is valid only up to the point of saturation. Once the field poles are saturated, phi will not increase with increase in IA. Even though I increases or armature current increases, phi will not increase proportionately. Only marginal change will be there. So T is proportional to IA square till saturation. So these are the relationships for shunt motor and series motor. For shunt motor, torque is proportional to armature current, and for series motor, torque is proportional to square of the armature current till the field poles are saturated. Now the power stages are VI is the input and draw a shunt motor also. Vi is the input. So the field current is If. So V into If is the power lost in the field winding, power dissipated in the field winding as heat, which is the field copper loss. And Ia square Ra, here in this case, this is Ia square Ra is the armature copper loss. So from the input, the copper losses are met. Copper losses are field copper loss and armature copper loss. Here it is the same. I into voltage across the field winding is the field copper loss, and I square Ra is the armature copper loss. So from the input, the copper losses are met, and remaining is the power developed by the armature. So remaining is Eb into Ia. Then from the power developed by the armature, rotational losses are met. Rotational losses means magnetic losses, that means core losses, eddy current and hysteresis loss, friction loss, bearing friction and brush friction, plus windage loss, friction with the surrounding air. So these losses are met. Rotational losses are met from the power developed, and remaining is the output. So Eb into Ia is also is equal to 2 pi n Ta. This equation we have used for deriving the torque equation. So Eb into Ia is equal to 2 pi n into Ta. Similarly, from Eb into Ia minus rotational losses is the output. So the torque available at the motor shaft can be found out by dividing output with 2 pi n. Or power developed divided by 2 pi n is the armature torque. Output divided by 2 pi n is the shaft torque. So the difference between these two is the rotational losses. Rotational losses divided by 2 pi n is the torque lost due to this friction, magnetic losses and windage losses. So rotational losses divided by 2 pi n is the torque lost. 2 pi Ta is the total torque developed by the armature, out of which a portion is lost, which is equal to rotational losses divided by 2 pi n. The remaining torque is available at the shaft, which is the shaft torque. So 2 pi n into armature torque is Eb into Ia. 2 pi n into shaft torque is output in watts. So this relation, see here we know that Eb is equal to V minus Ia Ra. So if we multiply throughout with Ia, Eb into Ia is equal to V into Ia minus Ia square Ra. Then substitute for Ia. Ia is equal to I minus If. Ia, this is the armature current, which is equal to I minus If. So we'll get Vi minus Vif minus Ia square Ra. That means input minus field copper loss minus armature copper loss is the power developed by the armature. So the relationship is like this. Vi is the input. This is the case of a shunt motor. So Vi is the input. From input, armature and field copper losses are met. Remaining is the power developed by the armature, from which rotation losses are met. Remaining is the output. For series motor also same relationship holds good. Vi is the input, then I square R is the armature copper loss. Voltage across the field winding into I, that is the field copper loss. So from input to these two copper losses are met. Remaining is the power developed by the armature. From that rotational losses are met. Remaining power is available at the shaft, or remaining is the useful output. Now the speed relations are, so we know that back EMF is equal to phi z NP divided by 60A. So we can generalize it. TB is proportional to phi into N, because rest of the parameters are constant for a particular motor. Or you can write N is proportional to EB divided by phi. And for shunt motor, since flux is constant, so during its operation from no load to full load, nothing or the field current is not changed, or flux is kept constant. So we can write the relation N1 divided by N2. N1 is proportional to EB1 by phi 1. N2 is proportional to EB2 by phi 2. In the case of a shunt motor, phi 1 is equal to phi 2. So N1 by N2 is equal to EB1 by EB2. But for series motor, we can write the relation N1 by N2 is EB1 by EB2 into phi 2 by phi 1. That is, N1 is proportional to EB1 by phi 1. N2 is proportional to EB2 by phi 2. So N1 by N2 is EB1 by EB2 into phi 2 by phi 1. Now let's work out a few examples. A DC shunt motor takes an armature current of 120 ampere at 500 volts. So terminal voltage is 500 volt. Armature current is 120 ampere. Armature resistance 0.2 ohm. Then the armature is lap connected with 850 conductors. So Z is 850. Number of poles 6. Then flux per pole is 0.05 Weber. Calculate the speed and armature torque. So here it is mentioned armature is lap connected. So A is equal to P. P is 6. So A is also equal to 6. We have to find the speed and the armature torque. So speed can be found from this relation. EB is equal to phi z NP by 60. For that, EB is to be found out first. So EB is equal to V minus IAR. Before that, let's mark the parameters in the diagram. This is 500 volts. IA is equal to 120 ampere. IF is not given. It's not required here. IA is equal to 120 ampere. R at 0.2 ohm. R is equal to 0.2 ohm. So EB is equal to V minus IARA. So the back EMF is equal to V minus IARA. V is 500, IA 120, R at 0.2, 476 volts. So that can be substituted in this equation. EB is equal to 5ZNP by 60. 476 is equal to 5.05 over Z 850 into N into number of poles. P is equal to 6 divided by 60. A is also 6. So speed will get it as 672 RPM. Then armature torque is equal to 1 by 2 pi phi ZIA into P by A. 1 by 2 pi phi ZIA into, this is a lap connected machine, number of poles and number of parallel paths are the same, so P by A is equal to 1. So torque we will get it as 811.7 Newton meter. Next example. A 250 volt 4-pole wave wound DC motor has 750 conductors. So V is equal to 250, number of poles 4. Number of conductors 750. The armature and series field resistances are 0.2 and 0.55. RA 0.2, RF 0.55. RA 0.2, RF 0.55. Armature current is 40 ampere. There's only one current here. It's 40 ampere. Flux per pole is 25 milliweber. So 0.025 weber. It is flux. Find the speed and armature torque. Same as in the previous case, but this is a series motor. That's all the difference. So 250 volt, IA 40 ampere. Then back EMF is equal to V minus IARA. Here back EMF is equal to V minus I into RA plus RF. In the case of series motor, EB is equal to, there is voltage drop here. This is RF, RA. This is the back EMF. This is the applied voltage. That is 250 volt. So this is I or IF or IA. IA, let's take it as IA. So this EB is equal to applied voltage minus voltage drop across the field winding, voltage drop across the armature resistance. These two are to be considered, or both the parameters are to be considered here. So back EMF is equal to 250 minus IA. IA is 40 ampere into RA plus RF. Both the resistances are to be considered here. So RA plus RF, RA is 0.2, RF 0.55, so total is 0.75. That is 220 volts. Again, state can be found from this relation. So EB is equal to 5 ZNP by 60A. EB we got, that is 220 volts. It's equal to 5 ZN P. P is 4 divided by 60. A is equal to 2 because it is a wave wound machine. So A is equal to 2. So A is equal to 4. So for solving this, N is equal to 352 RPM. Then torque is equal to 1 by 2 pi phi ZIA into P by A. So 1 by 2 pi phi ZIA. P is 4, A is equal to 2, so P by A is equal to 2. So armature torque is 230.73 Newton meter. Next example. Determine the armature torque and shaft torque. Armature torque, shaft torque and rotational losses of a 200 volt 4-pole series motor with 800 conductors. So applied voltage is 200 volt. Number of poles is equal to 4. Number of conductors 800. Armature is wave wound. Wave wound means A is equal to 2. It supplies a load of 6.5 kilowatts. That means output is 6.5 kilowatts by taking a current of 40 ampere. So input current or armature current is 40 ampere. Flux per pole is 0.025 weber. Armature resistance 0.2, field resistance 0.4. So we have to find out the armature torque, shaft torque and rotational losses. So armature torque 1 by 2 pi phi ZIA into P by A. It is 1 by 2 pi 5.025. Z is 800. IA is 40 ampere. into P by A. P is 4, A is 2, P by A is equal to 2. So armature torque is 254.65 Newton meter. Then speed can be found out from this relation. For that, EB is to be found out first. So EB is equal to V minus IA into RA plus RF. This is a series motor. So V minus IA into RA plus RF, that is V is 200 minus IA 40 into RA plus RF 0.2 plus 0.4, 0.6. You get it as 176 volts. So 176 is equal to, that is EB is equal to 5 set NP divided by 60A, for which from which N is equal to 264 RPM. Now speed we got it in RPM. So in RPS I'll write it as this divided 264 divided by 60. That is 4.4 RPS. Now shaft torque can be found out by dividing output with 2 pi n. So 2 pi n into shaft torque is the output in watts. So here output is given 6.5 kilowatts of 6500 watts divided by 2 pi n. N is the speed in RPS, or 2 pi into 4.4, 235.12 Newton meter. So rotational losses can be found armature torque minus shaft torque. So the difference between these two torques into 2 pi n, that will give the rotational losses. Here it is 540 watts. The output is 6500 watts. If you add these two, you will get the power developed, which is equal to EV into IA. So we got armature torque. We found out the speed. Then speed in RPS is found out. So output, we know it is given, that is output divided by 2 pi n will give the shaft torque. So difference between these two, armature torque and shaft torque, difference between these two is the torque lost due to core losses, friction and windage losses. So this torque in any case, torque into 2 pi n, speed is in RPS, will give the corresponding power in watts. TA into 2 pi n will give the power developed in watts. Then the lost torque into 2 pi n will give the rotational losses, 540. Shaft torque into 2 pi n will give the output. Your output is 6500 watts. So shaft torque is 235.12 Newton meter, and armature torque is 254.65 Newton meter. This is armature torque is 254 and shaft torque is 235. Difference between these two is the lost torque lost due to this rotational losses. This power developed is EB into IA. That is EB, we know the value of EB. 176 into IA is 40. 176 into 40 is the power developed in watts. Now next is a 220 volt shunt motor runs at 1000 RPM. P is equal to 220 volts, speed is 1000 RPM on no load and takes 6 ampere. No load current is 6 ampere. The armature and shunt field resistances are 0.25 and 220. Then calculate the speed when the motor is loaded and takes 40 ampere. When the motor is loaded, current increases. The increased value of current is 40 ampere. We have to find the speed when the motor is loaded. So circuit diagram, let's check. First case, I1 is 6 amp, V is equal to 220 volt. Then first case current is equal to 6 ampere, input current is 6 ampere. So I is equal to 6 ampere. Field resistance is given, armature resistance is also given. So armature and shunt field resistance 220 and 0.25. This is 220 ohm. This is 0.25 ohm. Ra is equal to. This is Rf. So we can find out the field current. 220 divided by 220. That is 1 ampere. So this is armature current. 6 minus 1 is equal to 5 ampere. Second case, 220 volt. Second case, input current is 40 ampere. So this current is 40 ampere. Field current is same 1 ampere. Rf is 220 ohm. So this current, armature current in the second case is 39 ampere. These are the conditions. Now in the first case, armature current is 5 ampere. We marked it already, 5 ampere. Then EB1 is equal to V minus IARA. V is 220. IA in the first case it is 5 ampere. RA 0.25 to 18.75 volts. Then in the second case, current is 39 ampere. So EB2 in the second case, that is 220 minus 39 into 0.25, 210.25. So for a shunt motor, EB1 by EB2 is equal to N1 by N2. EB1 is 218.75, EB2 is 210.25 is equal to N1 is 1000 RPM. So N2 we have to find from this equation. We get it as 961.14 RPM. So back EMF is to be found out in each case. So input currents are given. First case 6 ampere, second case 40 ampere. So first case armature current is 5 ampere, second case armature current is 39 ampere. So back EMF can be found out in the first case as well as in the second case. Speed here is given, this is 1000 RPM. So speed can be found in the second case. This is 961.14 RPM. N2 is next question. A 600 volt DC series motor takes 40 ampere and runs at 600 RPM. Find the speed when the load is reduced such that the motor takes 35 ampere. So Ra plus Rf is 1 ohm. So our total 1 ohm, Ra plus Rf. So V is 600. Current in the first case 40 ampere. Speed in the first case is 600 RPM. We have to find out the speed when motor is loaded. Motor is loaded, speed reduced, current is reduced to 35 ampere. So we can mark the parameters. This is 600 volt applied voltage. Here it is 40 ampere. Here it is 35 ampere. Total resistance 1 ohm. RT is equal to 1 ohm. RT is equal to 1 ohm. Field plus armature, both the cases. So we can find out the back EMFs. In the first case, 600 V minus IA into RI plus RF. 600 minus IA in the first case is 40 ampere into RI plus RF total is 1 ohm. So 560 volts. In the second case, 600 minus current is 35 ampere. 35 into total resistance 1 ohm. It is 565 volts. Now substitute in the equation N1 by N2 is equal to EB1 by EB2 into phi 2 by phi 1. N1 is 600 RPM, N2 we have to find out. EB1 560, EB2 565. Instead of phi 2, we have to write IA2. As it may be given in the question, assume flux is proportional to armature current. So we are asked to assume flux proportional to armature current. So instead of phi, we have to put the corresponding armature current. Instead of phi 2, we have to put IA2. Instead of phi 1, we have to put IA1. IA2 is 35, IA1 40 amperes. So from this, N2 can be found out, which is 691.83 RPM. Next example. A 6-pole 220 volt, number of poles 6, played voltage is 220, DC series motor has a wave wound armature, so A is equal to 2. With 496 conductors, set 496. Input current is 50 ampere, flux per pole 0.02, rotational losses 800 watts, and total resistance of armature and field 0.25. Find the gross torque, speed, and shaft torque. So gross torque or armature torque. Gross torque is the total torque developed. Out of that, a portion is lost due to rotational loss, due to rotation of the armature. And the remaining is available at the shaft. That is the shaft torque, which is the useful output. So armature torque is 1 by 2 pi phi Z Ia into P by A, 1 by 2 pi. Phi is 0.02. Set 496. 1 by 2 pi phi is Ia 50 ampere into P by A. P4A is equal to 2. P4A2. P by A is 2. 157.88 Newton meter. In back EMF is equal to V minus IAR 220 minus 50 into total resistance is 0.25. V minus IA into RI plus RF, that is 207.5 volts. So speed can be found from this relation. EB into IA is 2 pi n into TA, or n is equal to EB into IA divided by 2 pi TA. EB is equal to 207, IA is equal to 50, 2 pi T armature torque is 157.88. We will get it as 10.46 RPS or 627.84 RPM. 10.46 multiplied by 60. Then shaft torque is equal to, this is the armature torque, 157.88 minus rotational losses are given 800 watt. 800 divided by 2 pi n is the torque lost. So armature torque minus the torque lost is equal to 157 minus 157.88 minus 12.17. That is 145.71 Newton meter. So armature torque Then power developed by the armature is 2 pi n into 2a. From this equation, speed can be found. Then shaft torque is equal to armature torque minus rotational losses divided by 2 pi. Get it as 145.71 Newton meter. So that's all for today's session. Thank you very much for attending this session. If you like the session, please subscribe for the channel and press the bell icon for notifications.